Okay, let's start for our discussion for this LSST club about the near-field cosmology working group. Yeah, our speaker is Akasha. Is my pronunciation correct? Akasha.
Akshara.
Okay, sure. Okay. Is CITI Lansing Fellow and IU Group Foundation Fellow and the University of Victoria in Canada, I think. Yeah. Exploring the ancient history of the Milky Way through the most mid-polar stars and faint stellar streams. And sorry, her current work uses data from Gaia, Pristine, and Unis service along with the Wave, yeah, and the Euclidean service. I think also other future sky service such like LSST, yeah, and blending the observations with the cosmology simulations to trace the universe earliest and oldest stars and streams. And today she will give us something about the mapping the ancient Milky Way through the mid-polar stars and the stellar streams. Okay, let's go ahead. Kasha.
Thank you. Um, I'll share my screen.
Mhm.
Are you able to see my screen? Okay.
Yes.
Start slideshow. Cool. Thank you for the introduction and also the opportunity to speak here. I'm Akshara Vishwanathan. I'm a CETA Fellow and a Gruber Fellow at the University of Victoria in Canada. Most of what I am going to talk about is from my PhD that I recently finished in the University of Groningen, and a little bit of what I've been doing during my postdoc. Um, I thought I'll start with a little bit of an introduction. I'm Akshara. I'm from the south of India, a little city with about 12 million people. Um, and I pursued engineering when I was doing my bachelor's there, but I always wanted to do astronomy, so I went to different parts of India to do plasma physics and also to Victoria as a summer fellow to do Aegean and merger connection. And I went back to India, finished my bachelor's making wearable antenna, and then I got a master's in astronomy, finally in UK, where I did something completely different. I worked on gravitational waves and lensing of gravitational waves, and ended up in University of Groningen with a semester in Flatiron, working on galactic archaeology. And now I'm back in again in Victoria as a postdoctoral fellow. Um, so what the field that we work on is galactic archaeology. It needs no introduction probably for this audience, but just to give an idea, we all know that like any other galaxy, the Milky Way is accountable. It's cannibalizing all these little dwarf galaxies, merging with them, which creates a lot of chaos and star formation and mass growth, and even bar formation that a lot of simulations and predicts. See something in the chat. Okay, not for me. So this way our galaxy grows and we see it as we see it right now. But the halo of the galaxy is actually experiencing and depositing these dwarf galaxy mergers that the Milky Way had in the past. And so when we look at the halo and we disentangle these different merger events and accretion events that happens, then we're looking at really old stars, but also really old galaxies that the Milky Way merged onto. Um, and that's why this field is called galactic archaeology. Um, yeah. But how do we do this? For that, we need stars. Stars are great time machines. We can, just by looking at the motion and the chemistry of the star, we can see how many generations lived and died before the star, how massive were the progenitor galaxy that it was born in, was it a big or a small galaxy, and what type of supernova explosions happened close to the star. And if we look at an age-metallicity relation of stars that were born in the Milky Way, so in situ to the Milky Way, it will look something like this. So this is from the fire simulations of a Milky Way analog, and you can really see that when we look at really metal poor stars, so things that are below -2 decks and lower, we're looking at some of the earliest times of the universe, some of the first billion years of the universe, and that way understand the formation of the universe and the galaxy at once on a star-by-star resolution. Throughout this talk, I'll be using this term metallicity, so I thought I'll define it early on. Metallicity is in our field is mostly iron abundance that we use as a proxy for metallicity. So it's iron over hydrogen scaled to solar value. So 0 means it's sun-like metal contents. And metals are always, the abundance is heavier than hydrogen and helium. So as we know that most of our stars in the galaxy are metal rich. So they're either more metal rich than Sun or slightly more metal poor. Most of these stars are born in the disk as it settles. And there are stars in the halo and some in the bulge that are these more metal poor stars and old stars. But then these are very, very low in numbers. Only 1% of the Milky Way's number counts. And then you can really push this tail to extremely metal poor, ultra metal poor, hypermetal poor, mega metal poor stars, where we only know like 40 stars so far. And these could be the rare remnants of stars themselves, so the population 3 stars. So if we look at astronomers' definition of metallicity as the time went on, the hydrogen and helium gets ionized and you form more and more heavier elements. So as you look at, stars like the sun, you're looking at present day abundances, whereas these old stars would be some of the first stars that ever formed. And so that is chemistry. So for dynamics, I use mostly the Gaia survey, which was sent into its retirement orbit recently. So this was like the last observation of Gaia by an amateur astronomer. But Gaia survey is measuring position, proper motion, parallax, basically all of astrometry for about 2 billion stars in the galaxy. And it's also so much more stars, 10,000 more objects, but also much bigger volume and much more precise in its measurement of 5D positions and velocities. It also has a spectrometer, which I will be talking about a little bit later. But here is like a bit of an exaggerated video of how Gaia is resolving all of these 5 dimensions, like position, proper motion, parallax, and everything. Don't know if we'll see the... Yeah, so then you can sort of see the different constellations that make it up. But anyway, this is a more exaggerated version. It's not the reality. But Gaia is awesome. Moving on. So in galactic archaeology, we have at least 2 challenges. One is that we need large samples of halo stars, which only make up 1% of the galaxy's number count or mass count. And we need them with 6D phase-space data and chemistry whenever available. And we need large samples of very metal poor stars, which are also very, very rare, without having to serendipitously find them, because 1 in every 10,000 stars end up being very metal poor. So you want better technique to be able to select them. So for that, one of the things that we do is use Gaia's 5D data, so like position, proper motion, parallax, to be able to, so independent of distances and radial velocities, to be able to select halo stars. So for that, we use this reduced proper motion parameter, which when you plot against color, so this is color versus reduced proper motion, it has a relationship between apparent magnitude and proper motion, which in turn becomes a relationship between absolute magnitude and tangential velocity. So here you can basically imagine this diagram as a color magnitude diagram, but shifted at different tangential velocities up or down. So if we look at really high tangential velocity stars, which usually is random halo orbits, you can see that these high tangential velocity stars in its main sequence regime kind of isolate from the more disk-like stars, which is most of this figure. This is all of stars in the Gaia. So if I overlay a selection for that, we end up having more pure halo selection of high tangential velocity stars. And because they're main sequence stars, you also get very precise distances. So those, I aim to look at stellar streams, which I guess is also one of the main scientific interests of LSST within this group. So stellar streams are disrupting global clusters or dwarf galaxies, which when it is pulled by the gravitational tides of the Milky Way, start stripping along its orbit. So you can see this stream that is like stripping around the Milky Way's gravitational potential, which is shown as these contours in the background. So just based on its curvature, its orbit, and the way you see the stellar stream around the Milky Way as we observe it, you are able to say a lot about the Milky Way itself, the host, the mass of it, the gravitational potential, shape of the dark matter halo, but also like small scale perturbations that the stream has can tell us a lot about dark matter subhalos that perturb them or other baryonic perturbations. So if I let the stream integrate for longer and longer, you can also see that it kind of disperses. Initially, it's around its orbit, but the longer it makes many, many pericenters around the Milky Way, it completely disperses, and at one point you don't see the stream coherent anymore. You need better techniques to be able to pull it out. And streams are, I love streams, but I want to convince you all. So streams are important because they could be one of the most metal pore structures that we know of in the universe, like we do in the Milky Way, which is the C19 stream, which is the most metal pore stellar structure discovered yet. And these kind of small scale perturbations that I was talking about in dense streams, so star cluster disruptions, can actually tell us something about dark matter subhalo distribution in the galaxy. And stream not only dark matter perturb stream, but also other streams perturb these streams. There are baryonic things that perturb the streams, which can tell us something about the more massive stream that's perturbing it, or it could tell us something about the bar that's creating resonances with the stream, and we can learn more about the host galaxy just using these stellar structures. And there are just a lot of streams in the galaxy. We have too many, and it's only fair to make use of them to know more about the galaxy. One of the streams that I studied with this reduced proper motion halo catalogue that I am a fan of is the Jhelum stellar stream, which is in the southern sky. And if you look at the stream in stream coordinates, so you flatten it in which the x-axis is the longitude along the stream and y-axis is the latitude along the stream. And it doesn't look as simple as the other streams that I showed in my video, right? So it doesn't look like nice thin stream. It seems like there's too many different components in the stream. There's something more dense here, there's something a bit more diffuse, and you also see like a tertiary component. So now this is Gaussian smoothed. If I, okay, yeah, primary, secondary, and tertiary components. And if I don't Gaussian smooth it, it looks even more peculiar. You see a lot of breaks in its density distribution. You see a very major density break here. There's more clumps and gaps that we see, which is all a lot of information. And if we look at so these kind of density breaks, it could even be caused due to a progenitor completely dissolved when the stream is like stripping as a trailing arm and a leading arm around the galaxy. So what we wanted to do is to be able to reliably isolate these different components of the stream to understand what's happening, what is causing these different components in a stream. For that, we used, together with a PhD student here at the Institute in Groningen, we used this machine learning algorithm called locally aligned ants technique, which basically aligns, it was used for cosmic filaments, and then we modified it for streams, but it basically uses an ant following its food kind of technique to like actually probe linear structures. So that way we actually isolated like the component A and the component B, so the narrow component and the broad component. So here they're shown as red and blue. And you can see that the narrow component is not just narrow on the sky, but it's also narrow in its velocity distribution. You can see that it's much more tighter in the radial velocity compared to the broad component, which looks much more diffuse. You can see it a bit more in the inset here as well. So if we fit orbits to it, previously we couldn't fit one single orbit that would go through all the members of the Jhelum stream with its 60 members. But now, when we isolate the narrow and the broad component, we're able to independently fit an orbit that is most likely for the stream to have. And you can see that the narrow component here is basically narrow in every parameter. It's narrow in proper motions, it's narrow in on sky, it's narrow also in radial velocity. So this is indicative of the fact that maybe the narrow component was a globular cluster inside the broad component, which was a dwarf galaxy, both of which pre-processed and disrupted onto the Milky Way. This is something that we would expect for low mass dwarf galaxies and globular clusters anyway in hierarchical galaxy formation, but this is the first time we're actually seeing it in a stellar stream. Yeah, so I would keep talking about streams the whole time, but we have to move on. The other part of this talk is metal poor stars, right? So we want to, in order to select these very metal poor stars, we want to first understand how rare are these metal poor stars. So for that, we need a lot of halo stars with metallicities, but most of these halo stars within my reduced proper motion catalog goes to the limiting magnitude of Gaia, and there are no spectroscopic surveys that measure metallicities at that low, at that faint magnitudes. So for that, we use the Pristine surveys photometric metallicities instead of spectroscopic metallicities. Photometric metallicities, the way it works is very simple. To basically build a filter around a metal-sensitive line and get the flux out of it. And here we're using calcium H and K region in the Pristine survey from Magacam CFHD. And as you go more and more metal poor, the flux that comes out of this filter is going to be brighter for a metal poor star and fainter for metal-rich stars. So when you compare to a broadband, which means that we're able to easily pick up metal poor stars compared to a metal rich star, even though they are more and more rare in the galaxy. Pristine is bad weather program at the moment is a large program, so it's all over the sky and very, very much patchy. It's only in the northern sky. So we are with Pristine, we are deeper than Gaia, but we don't have a good coverage in the sky. Whereas with Gaia, we're able to do a similar technique. So with the recent data release, it released low resolution spectra, so it looks that low resolution, with which we can still use this calcium H and K region to get the flux out of and do the same technique of metallicity sensitive lines and what do they tell us about photometric metallicities. So when we do that, Gaia is shallower, but we are all sky at least. So we end up with these two amazing catalogues of photometric metallicities. Now I use the halo stars from the reduced proper motion catalog and cross-match that with the Pristine photometric metallicities to understand the low metallicity tail of the galaxy. So here I'm showing all the stars in Pristine in black and only the reduced proper motion halo in pink. And you can already see most of the metal-rich stars are gone because the halo is relatively metal poor, as you can see. And if I look at all the stars in our sample and only plot stars that are closer than 5 kiloparsecs, so solar neighborhood, we are able to see this kind of a fall off in the metal poor end, right? Like it almost feels like there's like an exponential decay. So we try to use an algorithm to automatically fit power law slope or a broken power law slope, depending on what the data prefers, to understand what is the slope of decline that we see in the metal poor end. And the data prefer to fit broken power law. So the break is around -2, where we see like between -1.5 and -2, we see relatively more metal poor stars, and below that, the frequency is even lower. And if we look at the solar neighborhood, only one in every 100, only one in every 10,000 stars end up being extremely metal poor. So this gives us an idea of how rare these metal poor stars are and where to focus and what will be the statistics of getting them when we survey the entire galaxy unbiased. And this slope also seems to change. It becomes more and more shallower as we go to larger distances, indicative of the fact that in the outer halo, we have a better chance of finding more and more metal poor stars. So now we know where we need to look for. We need to look at the outer halo when we want to study these metal poor stars. The outer halo is not just great for metal poor stars. There are a lot more things going on. For example, there's the Sagittarius stream, which was one of the first stellar stream discovered, which is disrupting around the galaxy. There's multiple wraps around, and this stream is mostly populating the outer halo. And there is the Large Magellanic Cloud, which is infalling into the galaxy. It's in its first pericenter orbit, we think of. And you can also see that this Large Magellanic Cloud, as it's infalling along with its dark matter, it is creating a sort of a transient wake in the Milky Way's dark matter halo. So there is basically an asymmetry in the dark matter distribution in the outer halo within our galaxy due to the infall of the Large Magellanic Cloud. And when there is a merger event, so this is a merger like Gaia and Enceladus, the last major merger with its own metallicity gradient, you can see how it like completely starts disrupting, right? And one of the things that's very easy to notice there is that with this metallicity gradient, it looks like most of the metal poor stars from this merger event is populating itself in the outer halo. So there is actually a bit of a metallicity gradient even within these dwarf galaxies that are disrupting inside the Milky Way. So also more of these accretion events and their metal poor tail is easier to probe in the outer halo. So for that, we were building an outer halo catalog of bright red giants. So for that, we use Gaia again. We use good parallax for starters. We're not using parallax to get distances, but we just want to put them on a color magnitude diagram and be able to reliably say whether it's a dwarf or a giant. So we only need good enough parallax for that. So we remove the dwarfs, we keep the giants. And within Gaia, we know for a certain magnitude limit, the dwarf or main sequence stars are so nearby that the parallax should be able to resolve them and give a good parallax, which means that within this magnitude limit, a star having a bad parallax automatically means that it's a bright red giant that is further away. So using this magnitude limit, we figured out what this magnitude limit could be. And within this magnitude limit, we automatically take all the stars with bad parallax as indicative of it being a giant. And we end up with a lot of stars that we're able to fit distances, photometric distances to using Basti isochrones, stellar parameters, and metallicities that we get from the Pristine survey. This way, we're going to up to like 100 kiloparsecs in the galaxy, which is quite nice. And one of the main things that we can do with a catalog like this is study the metallicity distribution, right? So you can basically plot height above the plane, so basically z, absolute z-axis, and a relative contribution of different metallicity bins. And it's immediately indicative that the inner halo is much more smoother in terms of substructure because most of the streams and most of the merger events completely disperse and are not coherent. Whereas the outer halo is very, it's not phase mix completely. It's very non-linear. You can see a lot of substructures already in this plane. You can see Sagittarius in the more metal-rich end. You can see apocenter pileups of Gaia and Enceladus and intermediate metallicities. And in the outer halo, about 40% of the stars end up being very metal poor. And we can also correct for selection effects. I don't want to get more into the details, but we can talk about it later. Because these selections are all based on colors and these are magnitude limited samples, at different distance bins and at different metallicities, we're probing different parts of the isochrone. So we're missing a lot of metal rich stars compared to metal poor stars. So this is a selection effect that we need to correct for. So after correcting for those, we are able to get this sort of a metallicity distribution map of the galaxy. One of the main things that I was interested in with this catalog is literally just look at the outer halo, plot every star in the outer halo, and see what's happening given this nonlinear distribution. And with this, we are able to immediately see, I'm kind of indicating your eyes towards it, but like even without these lines, you're able to see like an overdensity of stars here, which almost looks like it's emanating from the large and the small Magellanic clouds. So what we did is to sort of select these stars, and we realized that all of these stars are very metal poor, so everything is below -2. And we sent it out to observe with the Gemini Ghost telescope. This we think is the stellar counterpart to the Magellanic Stream. So Magellanic Stream, as shown in this N-body simulations, is the sort of a gaseous stream that we found like about 5 decades ago in gas. I'm just going to play it again, which kind of is populating its trailing arm in the southern part and the leading arm in the north. And we think this could be due to the tidal interactions between the Magellanic clouds as it's falling into the galaxy. But we never found a stellar counterpart to it until very recently, and we think this could be a very metal poor end of this Magellanic stellar stream. And with Gemini Ghost during my postdoc, we have gotten new observations of radial velocities for these stars, but also we're analyzing for metallicities and other chemical abundances. But you can see in Magellanic longitude and latitude, these stars are all having tangential vectors pointing towards the clouds. You can see that the radial velocity is also completely following what you would expect from models that are based on the gas Magellanic stream. So there's a lot of interesting stuff going on with this that I'm very curious about. And in the outer halo, we also have a lot of substructures, like I said, are completely phase mixed, that you cannot see them as coherent substructures in streams on sky. For that, we need conserved quantities or velocities. So conserved quantities could be energy and angular momentum, which are integrals of motion. In an axisymmetric galactic potential, you would expect them to be conserved over many, many gigayears. So all these merger events should still remain as clumps in this distribution. So this kind of reminds me of immigrant population in New York, how they're really clustered at different parts of New York. So when we look at that in photometric metallicities on the left, and simultaneously there was a work using H3 survey with spectroscopic metallicities on the right, you can really see that photometric metallicities are doing a very good job. You still see this hot thick disk. For easiness of your sky, I'm just gonna invert this plot so their disk is on the same axis as ours. But you can see that there is still the hot thick disk stars. You can see Sagittarius being more metal rich, Gaia and Enceladus populating the more isotropic halo, and other more metal poor major events like Sequoia on the retrograde halo, which was very convincing to see given that we don't know how much we can trust photometric metallicities as values. But that's not all we need, right? We need a more quantitative approach to seeing how well the metal poor photometric metallicities perform. So for that, we look for them in large spectroscopic surveys. So we look for all of our very metal poor stars and see what the spectroscopic surveys say about them, or we do dedicated follow-up of very metal poor stars ourselves. So the first thing that we did is to use these photometric metallicities and look for how they're performing in spectroscopic surveys. But then we realized that most of the spectra from very metal poor stars in large spectroscopic surveys are mistakenly classified as hot stars, or the automated pipeline says it's too noisy, or there's simply just no lines to fit, so no solutions. So then as a group, we started building this trasher of very metal poor stars, wherein we looked at different spectroscopic surveys, and we basically picked out the very metal poor stars that they are not able to analyze, and we reanalyze with more dedicated pipelines for that. One of the things that I led within that is to use Gaia RVS spectra and reanalyze the publicly available RVS spectra to get better metallicity. So on the top, you can see what Gaia GSP spec metallicities are given, and it's like all over the place, especially without a quality cut. Whereas with no quality cut, nothing, just using the spectra, we're able to get like really good metallicities for these stars that have publicly available archival spectra. And then we also need to dedicatedly follow up these stars to understand how well we're performing. So that I led a long-term program at the Isaac Newton Telescope in La Palma, focusing on near-infrared region, and then we later used optical region to get metallicities. We started with the stellar streams follow-up for this program, and then we had a lot of bad weather and a volcano eruption, and then we switched on to bright, very and extremely metal-poor candidates from Pristine, and things started looking up, and we had quite nice results, I think. So the target selection is very similar. We select good and bad parallax red giants, and they're all bright enough. They're all in the northern sky, given that it's INT in La Palma. And we basically look for metallicities, basically a spectroscopic metallicity that's in comparison with photometric metallicities. It looks like the distribution is quite good for both Pristine measurements, but also Pristine Gaia version of it. It looks like our very metal poor stars are bona fide very metal poor candidates. However, the scatter is much more lesser for Pristine measurements, which is not surprising because it's better in quality. So our success rate is 97% for picking up very metal poor stars, and about 38% for picking up extremely metal poor stars, so below -3. If these numbers don't convince you, a decade ago, this number was 2%. So I think we're doing very well, mostly because Gaia is helping us weed out a lot of very bad outliers, so catastrophic outliers. With these kind of catalogs, one of the amazing science that we can do is to look for substructures and streams that are extremely metal poor. One such stream that was found using Pristine and stream finder algorithm is the C19 stream, which has a mean metallicity of minus 3.34. So it is at least less than 1,000 of the 1/10,000th of the solar metallicity. And it is also at least 1 dex more metal poor than the known globular clusters in the Milky Way, and given its metallicity dispersion, we think that it could be a disrupting globular cluster. We, of course, had a lot of metal poor stars in the northern sky, so we were thinking, did we serendipitously find any C19 stars? So here I'm showing RA declination and declination versus rate of velocity. So I'm overlaying some of the known members of C19 and an orbit that we know of for C19 from Stream Finder, and I'm overlaying the new members that we think we've found for C19. What was very surprising is that we're finding a member like all the way above the disk, which is like about 50 degrees away from the stream, which now makes it a very long stream and very wide as well, which is not what you would see for a global cluster stream. So really with this kind of dedicated follow-ups, we're probing all this trail of breadcrumbs left by C19. If you're interested, there's also a new paper by GD-1 which looks at more stream members all across the sky and shows how long the stream is. But chemically, this stream shows this kind of sodium variation that you see here and like very narrow metallicity distribution that is indicative of global cluster, even though dynamically it doesn't seem like that. So it's really a bit of a puzzle what's caused C19 the way it is. Why is it important? Why do we even need to care? C19 must have formed very, very early, even less than 1 gig-year from the formation of the universe. So this really gives us a window into the formation of very first structures on a star-by-star resolution in our local neighborhood, complementary to what we can do in the high redshift universe. But also we found this one stream, but is it just the tip of the iceberg, or are we going to find more and more of these structures? Taking a small shift is the last part of my talk. We also looked at the orbits of these very and extremely metal poor stars that we followed up with our spectroscopic survey. So here I'm showing apocenter, what is the maximum distance the stars can go, and Z max, which is what is the maximum vertical extent it can go. And that's the forbidden region, as we know. These are stars very, very confined to the center, which is bulge, and confined stars, and inner and outer halo stars. What was more surprising was these confined stars. We seem to see at least 20% of the stars being confined to the disk, so they're moving like a disk star, which is more in number compared to an isotropic distribution of the halo in the metal poor end. So it automatically probes the question of, did the Milky Way have a very metal poor disk? And we see this sort of thing in high redshifts. We see more massive galaxies having very high rotation. And we also see within the Milky Way a lot of works that are showing that maybe we have a lot of stars that are moving like a disk. So what we can do with that, with large sample of stars in the Milky Way, we can look at metallicity and circularity. Circularity is basically how circular your orbit is for a disk-like star. So 0 means it's isotropic, 1 means it's moving like a disk, -1 is moving like a disk but retrograde. So we can disentangle this plots it's a bit more confusing, so we can disentangle it bin by bin in metallicity. So the metal poor end, we are, it's a very light line, but if you can see it, it doesn't look isotropic already. I am tempted to fit another Gaussian here. And we go more metal rich, this Gaussian is becoming more and more prominent, more, and then the disk forms. So we really see that there is this accreted isotropic distribution around 0, but we also see something which is the in situ proto-Milky Way that then becomes the disk, which has quite a bit of rotation already in the metal poor end. So this is just by eye, right? Like we also developed an algorithm to do something similar to a Gaussian mixture model, but as a conditional probability distribution. So it carries over information from every metallicity bin. using Jackson and Pyro. And here I'm showing metallicity versus circularity or sigma circularity, and metallicity versus fractional contribution of the spin-up versus the halo. So this is the in situ component, this is a halo-like component. You can see that the halo is isotropic, so 0, and it has quite a high dispersion in its circularity. Whereas the spin-up component, or this in situ Milky Way component, has quite high circularity for a very metal poor end already. It has 60% the circularity of the galactic disk. And the dispersion also gets lower and lower, as you can see, and the circularity becomes higher and higher. This is indicative of maybe there could be some more rotation in the early Milky Way than we thought there was. So the future is, I'm very excited to look for star streams in the outer halo. As you can all agree that is amazing. And we don't know of many star streams in the outer halo, as you can see here, and that is a discovery space. And we need chemistry. We need good chemical abundances for a lot of the outer halo stars to be able to understand these small accretion events that the Milky Way had. But we also need a census of accretion. We should be able to tell how many of these small mergers are we looking for. And that is something that we can do with metallicity distributions, we think. So the future is bright, and I look forward to exploring it together. Thank you.
Appreciate very nice talk. Yeah, so it's a good summary of the two groups from the Groningen and the Swansburg's progress.
Yeah.
I have a lot of questions, but I let the other colleagues to ask first. Do you have any questions, online audience? Questions? Okay, maybe I ask the first one is because I noticed the. Okay, Simon.
I have a hi, very nice talk. I have a question about C19. If it's true that it is pretty old, how can it is still so thin? It
Yeah.
doesn't. It does not dispersed in the halo, because if it is more than 10 gig a year, it should have been dispersed by the circulation and by the halo field, gravitational field. So I
Yeah.
don't know
No.
what is the answer.
No, I think that's a completely fair question. To be honest, I don't. We are not sure exactly why it survived, which is a puzzle as well. How does this go? Because it still look thin and nice, but it also looks more complicated than that because dynamically there are so many members across the sky. It's a long stream, and we think that maybe it came in with its own dark matter halo, with the stellar counterpart being just the star cluster. Or maybe it just formed in a completely different filament and somehow came in with a more recent accretion event, which could be a possibility. But it is a very big puzzle how it survived. But it has to be a global cluster because the chemistry says that it has to be a global cluster. So it will be very much impossible to expect it otherwise. So I think it is a bit of a puzzle, but it's a bit hard to say why it's surviving. Maybe it's very, very low mass that it took a lot of time to, it will take a lot more time to completely phase mix.
Okay. If I may ask another question. When you show the Gaia classification you did using the filter with the spectra, I've not understood if it how you calibrated it. You did the calibration using Pristine or using the known metal poor stars?
We did the photometric
If I
calibration.
understood exactly what you did.
Yeah, we did the photometric calibration using Pristine, but we do have a training sample of spectroscopic metallicities for each of these stars that we know from literature, but also from our own follow-ups of very metal poor stars. So we kind of pile up them all into a training sample. And based on the Cauchy-Matchke magnitude, we get metallicities for them using that. But the photometric calibration is made using what we know from Pristine. If that answers your question, maybe. I don't know.
Yes. Okay, thank you.
Okay.
Are any other questions or comments? I noticed that you have some sky coverage and footprints for the Princeton sky survey, and it also covers some regions in the southern sphere. So my question is that combine the LSST, high precision photometry, purple motion, and other catalogs. Do you have any ideas or suggestions or comments for us to how to do the synergy? Between the Princeton and the LSST to do more about the galactical archaeology or dynamicals. Mm.
Yeah, there is not that much coverage in the south, to be honest. But yes, we did have a separate bulge survey that is led by Anke Aronsen. We do have that is what you mean, I think, when you say let me just go back. It's gonna be a while. But we do have a coverage in the bulge and also part of M54, where we've done a lot of work, and I think it would be very good to. It's not coming. Anyway, it'll be very good to do something. I have not thought about it myself, actually. That would be awesome to be able to get, because we do go deeper than Gaia, but we are still a little bit tied to Gaia because we need broadband magnitudes, but we probably don't need that from when LSST begins. But also LSST has its own U band, which I'm hopeful that we can get photometric metallicities for as well. Not as good as Cauchy-Matchke, but to tell if something is full ground or very metal poor, it should definitely be possible. But yes, this is a more dedicated sub-survey within Pristine, and it is something that we can for sure think about as a synergy with LSST. Thanks for pointing that out.
Yes, and the second question is, and I also noticed that you focus on the mid-pool streams, in the inner halo and in the outer halo. Did you consider something about the initial mass function and some star formation rate? Yeah, from these mid-pool stars, in the stream. I think it's pretty interesting to discuss something, about the initial mass function of these mid-pool stars, I guess. Yeah. Mm.
Yeah, I think at this point I probably should. I haven't so far, but this is a question I've been asked already in a colloquium. So it is something that we should think about, especially given that we're finding more and more of these very metal poor streams. So C19 is not the only one. There's the Phoenix stream. There is one more stream that we think is below global custom metallicity floor. So we should. I'm not an expert in initial mass function, but I think it's something that we should think about for sure as an implication for IMF. I don't think people have done that with C19. It is something to do.
Yeah. Okay. Other questions? Ava.
Yeah,
Yes.
can you hear me? And I have a very simple question. And I noticed that you showed one of the figures about the substructures, and you found in IOM space, energy space, that you find many substructures, and you can see. And I'm curious about the sample you use is the PGS giant stars you mentioned.
Yeah, I use
Yeah.
the giants in the outer halo from this outer halo catalog basically, which is very similar to what's being used in this paper as well, using the H3 survey. They also use outer halo stars to make this sort of figure.
Okay.
Which is, and I forgot to mention this, but everything that I've talked about are catalogs that are made public from my work. So if anyone wants to use it, they're all there.
Okay, thank you.
I also don't have idea how you consider selection effect. You mentioned in one page you did the selection correction to do to the.
Yeah.
So how do you do that? Yeah,
Yeah, so we did something quite basic, but we realized that no one else does anything about it. But
uh-huh.
what we do is basically take model isochrones from Parsec, and we populate it across the metallicity distribution, assuming an IMF. And we say that I'm doing this color cuts, and at different distances, I'm probing different parts of the isochrone. So we basically say at this distance, at this metallicity, how much percentage of the isochrone am I probing in each metallicity? And we create a weight based on that, and we multiply that weight to our metallicity bin. So then you can basically correct for the fact that there is an overrepresentation of metal poor stars inherently as compared to metal rich stars. Because, for example, in this the most distant bin, we're not probing any minus 0.5 stars, which is not real, but more because we are using this color cuts for FGK stars. So this then gives us an idea of like, okay, what actually would the MDF look like?
The last question from my side. I noticed you have an algorithm RAAT, right? RAAT algorithm, could it be used to the LSST data?
Could it be used for which data? Sorry.
For Rubin data, for the LSST, the Rubin data.
Could it be used for AAT? I've personally not used AAT myself.
Oh no,
I think there are
no.
more experts in the audience here about that.
My question is then could it be used to the LSST data, the current
Oh,
the current DP1 or the other catalogs in the future from the Rubin observatory? Yeah.
I would imagine so, yes. Also, there is Foremost as well in the south, which is also a multi-object spectrograph.
For most is the spectroscopical. Yeah,
Yeah.
the LSST is the photometric data.
Yeah.
I'm not sure whether it can be used.
Maybe I'm not understanding your question. Are you asking if these photometric metalicities could be used for LSST? Or
Yeah.
yeah, absolutely. Yes, I think that is something to think about for sure.
Okay. Do you have any other questions? Massimo, do you have anything to see?
Unfortunately not, because I was absolutely late for the beginning of the talk, so I'm really sorry. But the results are quite amazing. So it is we're expecting a lot of fun. I was just wondering about the use of LSST. If, for example, if you have a guess about the contribution from the LSST proper motion. I'm asking because you know that Rubin will cover with proper motions range in magnitude, which is not covered by Gaia because of the photometric depth. And if the expected accuracy from Rubin is enough for your investigation.
I think definitely, because not just the proper motion beyond Gaia's limiting magnitude, but even like within Gaia's limiting magnitude, the proper motion quality gets so bad that at that point you can use the proper motions more to remove the foreground than actually select substructures themselves. So I think even just to improve that, that would be great. And also to go fainter, which means that I think I remember writing this up for some postdoc proposal, but I think we should be able to get good proper motions up to like 300 kiloparsecs in the red giant branch. And for streams discovery, we should be able to probe the turnoff at like 100 kiloparsec, which is just mind-blowing. This is definitely would be very useful. I think I'm also very much curious to see or maybe even investigate how much we can do with the U-band for photometric metallicities. I think that is
Exactly. This,
Maybe a game changer. Yeah.
absolutely, I absolutely agree about you, Ben. There is a huge expectation on that. Yeah.
Yeah. Yeah. I
Thank you.
agree. Cool.
Okay, if no more question, we see you next time, and I will stop the